Welcome to our exploration of motion in a plane. In this chapter, we'll dive into the fascinating world of two-dimensional motion, where objects move not just in a straight line, but across a plane. This type of motion is all around us, from a football soaring through the air to a car turning a corner. Understanding motion in a plane helps us analyze and predict the paths of moving objects in real life. Let's begin by laying the foundation for what motion in two dimensions really means, and why it's so important in physics. Motion in two dimensions refers to the movement of an object along a path that can be described using two coordinates, typically x and y, unlike one-dimensional motion, which is restricted to a straight line. Two-dimensional motion allows for more complex trajectories, such as curves and circles. This concept is essential for understanding real-world scenarios, like a ball being thrown or a car navigating a bend. By analyzing both the horizontal and vertical components, we can fully describe and predict the motion of objects in a plane. Understand motion in a plane, we need to distinguish between two fundamental types of quantities, scalars and vectors. Scalars are quantities that have only magnitude, such as speed or distance. Vectors, on the other hand, have both magnitude and direction, like velocity or displacement. This distinction is crucial because direction plays a key role in two-dimensional motion. Recognizing whether a quantity is a scalar or a vector helps us apply the right mathematical tools and concepts when analyzing motion. Let's clarify the difference between scalar and vector quantities. Scalars, like temperature or mass, are described by a single value. They don't involve any direction. Vectors, such as force or velocity, require both a value and a direction to be fully described. For example, saying a car moves at 60 km/h is scalar, but saying it moves at 60 km/h east is a vector. This distinction matters because vectors allow us to represent more complex movements, especially in two-dimensional motion. One way to add vectors is by using the triangle law. According to this law, if two vectors are represented as two sides of a triangle taken in order, their sum is given by the third side, taken in the opposite order. This graphical method helps visualize how different vectors combine to produce a resultant vector. It's especially useful in physics problems where forces or velocities act at angles to each other. Let's see how this works with a simple example. Another method for adding vectors is the parallelogram law. Here, two vectors are drawn from the same point, and a parallelogram is constructed with these vectors as adjacent sides. The diagonal of the parallelogram, starting from the same point, represents the resultant vector. This approach is particularly helpful when dealing with vectors that are not aligned along the same line. It provides a clear geometric way to determine the combined effect of two vectors acting simultaneously. The solution of vectors is the process of breaking a single vector into two or more components, usually along perpendicular axes like x, and why this technique allows us to analyze the effect of a vector in each direction separately. For example, a force acting at an angle can be split into horizontal and vertical components. By resolving vectors, we simplify complex problems and make calculations more manageable, especially when dealing with motion in a plane. Resolve a vector into components, we use trigonometry. Suppose a vector makes an angle theta with the horizontal axis. Its horizontal component is found by multiplying the vector's magnitude by cos theta and the vertical component by sin theta. This method allows us to express any vector as the sum of its x and y components. By working with these components, we can analyze motion and forces in each direction independently, making problem-solving much easier. Projectile motion is a classic example of motion in a plane. It describes the path of an object thrown into the air, moving under the influence of gravity alone. The trajectory is typically a curved path called a parabola. Examples include a ball being kicked, a stone thrown, or water sprayed from a hose. Understanding projectile motion helps us predict where and when an object will land, which is crucial in sports, engineering, and everyday life. Equations of projectile motion allow us to calculate an object's position and velocity at any point along its path. These equations are derived by analyzing the horizontal and vertical components separately. The horizontal motion is uniform, while the vertical motion is affected by gravity. By combining these two motions, we can predict the complete trajectory of the projectile. These equations form the backbone of solving projectile motion problems in physics. Range of a projectile is the horizontal distance it travels before hitting the ground. This distance depends on the initial speed, the angle of projection, and the acceleration due to gravity. By using the equations of motion, we can derive a formula for the range, which helps us predict how far a projectile will go. Understanding range is important in sports, engineering, and even in designing safety measures for various activities. Maximum height of a projectile is the highest point it reaches during its flight. This value is determined by the initial velocity and the angle at which the object is launched. By analyzing the vertical component of motion, we can derive an expression for the maximum height. Knowing this helps in planning trajectories and ensuring safety in activities involving projectiles, such as sports or engineering projects. Time of flight is the total time a projectile spends in the air from launch to landing. This duration depends on the initial velocity, the angle of projection, and gravity. By analyzing the vertical motion, we can derive a formula for the time of flight. This concept is essential for predicting when a projectile will land, which is important in various fields, from sports to engineering and safety planning. Uniform circular motion refers to the movement of an object in a circle at a constant speed. Even though the speed remains the same, the direction of motion changes continuously, which means the object is always accelerating. This type of motion is seen in many real-life situations, such as a car turning around a curve or the Earth orbiting the Sun. Understanding uniform circular motion is key to analyzing forces and accelerations in circular paths. Centripetal acceleration is the acceleration experienced by an object moving in a circular path, directed towards the center of the circle. This acceleration is necessary to keep the object moving in a circle, rather than flying off in a straight line. The magnitude of centripetal acceleration depends on the speed of the object and the radius of the circle. Understanding this concept helps explain why objects follow curved paths and is crucial in designing safe roads and amusement park rides. Centripetal force is the force that keeps an object moving in a circular path. It acts towards the center of the circle and is responsible for changing the direction of the object's velocity. Without centripetal force, the object would move off in a straight line due to inertia. This force can be provided by tension, gravity, friction, or other means, depending on the situation. Understanding centripetal force is essential for analyzing circular motion in physics. Circular motion isn't just a theoretical concept, it's everywhere in our daily lives. Think about a washing machine spinning clothes, a car taking a roundabout, or a child on a merry-go-round. Even the motion of planets and satellites involves circular paths. Recognizing these examples helps us appreciate how the principles of circular motion apply to real-world situations and why understanding them is so valuable. Relative velocity is the velocity of one object as observed from another moving object. It's a concept that helps us understand how motion appears different depending on the observer's frame of reference. For example, if you're sitting in a moving train and another train passes by, the speed at which you see the other train is its relative velocity. This idea is crucial for analyzing motion in situations where multiple objects are moving simultaneously. In one-dimensional motion, relative velocity is straightforward. If two objects are moving along the same straight line, the relative velocity of one with respect to the other is simply the difference between their velocities. This concept helps us solve problems where two objects move towards or away from each other, such as cars on a highway or boats on a river. It's a fundamental idea that lays the groundwork for more complex scenarios. When objects move in 2 dimensions, calculating relative velocity becomes a bit more involved. We need to consider both the x and y components of each object's velocity. By breaking down the velocities into components and then subtracting them, we can find the relative velocity vector. This approach is essential for analyzing motion in planes, boats crossing rivers, or airplanes flying in windy conditions. Vector analysis is a powerful tool in physics. It allows us to break down complex motions and forces into simpler components, making calculations more manageable. By using vectors, we can accurately describe motion in any direction and solve problems involving multiple forces or velocities. This approach is fundamental to understanding and predicting the behavior of objects in motion, from simple projectiles to complex machinery. Vectors are not just abstract mathematical tools, they're part of our daily experiences. When you walk north at a certain speed, or when a plane flies east with a wind blowing from the north, you're dealing with vectors. Understanding how vectors work helps us navigate, plan routes, and even play sports more effectively. Recognizing vectors in everyday life makes physics more relatable and practical. Vectors are often represented graphically as arrows. The length of the arrow shows the magnitude, while the direction of the arrow shows the direction of the vector. This visual representation makes it easier to add, subtract, and resolve vectors. By drawing vectors to scale, we can solve many physics problems graphically, which is especially helpful for understanding motion in a plane. When more than 2 vectors need to be added, we can use the polygon method. In this method, each vector is drawn in sequence, starting from the end of the previous one. The resultant vector is then drawn from the start of the first vector to the end of the last. This method extends the triangle and parallelogram laws to multiple vectors and is useful in complex motion and force problems. Subtracting vectors involves adding the negative of a vector. Graphically, this means reversing the direction of the vector to be subtracted and then using the triangle or parallelogram law. This operation is important for finding relative positions, velocities, or forces, and is a key part of vector analysis in physics. Multiplying a vector by a scalar changes its magnitude, but not its direction. For example, doubling the speed of a car doubles the length of the velocity vector, but the direction remains the same. This operation is useful for scaling forces, velocities, or other vector quantities in physics problems. Unit vectors are vectors with a magnitude of 1, used to indicate direction. They are often represented by symbols like I, J, and K for the x, y, and z axes, respectively. Unit vectors help us express other vectors in terms of their components, making calculations and representations much simpler in physics. The dot product is a way to multiply two vectors to get a scalar. It's calculated by multiplying the magnitudes of the vectors and the cosine of the angle between them. The dot product is useful for finding work done by a force or projecting one vector onto another. It's a fundamental operation in vector analysis. The cross product of two vectors results in a new vector that is perpendicular to both original vectors. The magnitude is given by the product of their magnitudes and the sine of the angle between them. The cross product is important for calculating torque, angular momentum, and other vector quantities in physics. Displacement is a vector quantity that represents the shortest distance from the initial to the final position of an object, along with the direction. Unlike distance, which is a scalar, displacement gives us more information about the actual change in position. This concept is crucial for analyzing motion in a plane. Speed is a scalar quantity that measures how fast an object is moving, regardless of direction. Velocity, on the other hand, is a vector that includes both speed and direction. This distinction is important in two-dimensional motion, where direction changes can affect the overall motion even if speed remains constant. Acceleration in a plane is a vector quantity that describes how the velocity of an object changes with time, both in magnitude and direction. It's essential for understanding how objects speed up, slow down, or change direction in two-dimensional motion. Analyzing acceleration helps us predict future motion and solve complex physics problems. Forces in two dimensions can be analyzed by resolving them into components along the x and y axes. By doing this, we can apply Newton's laws of motion to each direction separately, making it easier to solve problems involving multiple forces acting at different angles. This approach is widely used in engineering and physics. An object is in equilibrium when the sum of all forces acting on it is 0. In two dimensions, this means the vector sum of forces in both the x and y directions must be 0. Understanding equilibrium is essential for analyzing structures, bridges, and any system where stability is important. When a projectile is launched horizontally from a height, its initial vertical velocity is 0. The horizontal motion is uniform, while the vertical motion is accelerated due to gravity. This scenario helps us understand how different components of motion combine to create a curved trajectory. When a projectile is launched at an angle, both the horizontal and vertical components of velocity are non-zero. The path is a parabola, and the analysis involves resolving the initial velocity into x and y components. This type of motion is common in sports and engineering applications. In real-world situations, air resistance affects the motion of projectiles and objects moving in a plane. Air resistance opposes the motion, reducing range and altering the trajectory. While basic physics problems often ignore air resistance, understanding its effects is important for accurate predictions in engineering and sports. Non-uniform circular motion occurs when an object moves in a circle, but its speed changes. This means there is both centripetal and tangential acceleration. Analyzing this motion is more complex, but it's important for understanding real-world scenarios like cars accelerating around curves or amusement park rides. In circular motion, acceleration can be split into tangential and radial, centripetal components. Tangential acceleration changes the speed, while radial acceleration changes the direction. Understanding these components helps us analyze more complex motions and design safer vehicles and rides. Projectile motion principles are widely used in sports, engineering, and even in predicting the paths of fireworks. By understanding the equations and factors affecting projectile motion, we can design better equipment, improve safety, and achieve more accurate results in various fields. Classic example of relative velocity in two dimensions is the riverboat problem. Here, a boat tries to cross a river with a current. By resolving the boat's velocity and the river's velocity into components, we can determine the actual path and time taken to cross. This problem illustrates the importance of vector analysis in real-life navigation. Similar to riverboat problems, airplanes flying in windy conditions require vector analysis. The plane's velocity and the wind's velocity combine to determine the actual path and speed over the ground. Pilots use these calculations to plan routes and ensure safe, efficient travel. We've covered the essentials of motion in a plane, from vectors and their operations to projectile and circular motion. Understanding these concepts allows us to analyze and predict the motion of objects in 2 dimensions, which is vital in physics and many real-world applications. Mastering these ideas sets the stage for more advanced topics in mechanics. The key takeaways from this chapter include understanding the difference between scalars and vectors, mastering vector addition and resolution, and applying these concepts to projectile and circular motion. These tools are fundamental for solving physics problems and understanding the world around us. With a solid grasp of motion in a plane, you're now ready to tackle more complex topics in physics. The concepts learned here will serve as a foundation for understanding forces, energy, and momentum in greater depth. Stay curious and keep exploring the fascinating world of physics.